Earth's weather is packed with devastating power.
Oh my God!
The amount of energy that's released is beyond human comprehension.
But in the cosmos, Mother Nature's fury is unimaginable.
You think it's hot here on Earth? You ain't seen nothing yet.
Batten down the hatches.
If one of these were to happen today, it would shut the world down.
Because we're taking you into the heart of the universe's biggest superstorms.
The storms we see out in the universe are mind-blowing.
Over the next hour, we're chasing the biggest storms in the universe. We'll start with the staggering powers of Earth's worst weather. The heat, wind, lightning, tornadoes, and hurricanes that can change landscapes and lives in a heartbeat. And when we travel out into space, we'll see that Earth's weather is nothing compared to other planets. Weather like 17,000 km/h winds, or storms of raining liquid methane. We'll learn how scientists can actually forecast weather in deep space and discover why we need to be on the lookout for cataclysmic space weather that could cripple all life here on Earth. The reason most of us sit through our local weather forecast, half listening to the talk of barometric pressure, is simply because we want to know what to wear tomorrow. What's the weather going to be like in our little neck of the woods? It's a good question, because at any given moment on Earth, wildly different weather events are occurring. Thunderstorms and heat waves, drizzles and blizzards, tornadoes and clear blue skies. So what is weather? And where does it come from? Before you can answer that, you have to know something about our atmosphere. Our atmosphere is the air we breathe. It's the skin of gases wrapped around our planet, and it's very thin.
Many people think the atmosphere is really thick. We look up and the air seems to go on endlessly. Not exactly true. If this basketball were the Earth, and I were to submerge it, the thickness of the layer of water on this ball right now represents the thickness of the atmosphere.
Like the inside of our planet, the atmosphere has layers. They extend up to about 800 kilometers, but most of the gases in it, 99% of them, are located within 100 kilometers of the Earth's surface. And it's within this zone where all the weather occurs.
Weather is the personality of Earth's atmosphere. It's caused by the sun heating various parts of our atmosphere to different temperatures.
Those different temperatures lead to different air pressures. Warm air rises, cold air sinks, and weather is what happens when the atmosphere tries to even things out. Masses of air crash into each other and fight it out, trying to reach pressure equilibrium. And those battles result in Earth's most intense weather.
At its simplest, you can really think of weather as an atmosphere trying to balance itself. If one part is hotter, then it's going to expand. Well, that air has to go somewhere. If another part is colder, things will sink down. So weather is just things coming to an equilibrium.
Mother Nature's attempts to achieve balance can have deadly results. But surprisingly, the most dangerous thing she can throw at us isn't lightning, tornadoes, or hurricanes. What kills more people than all of those events combined is the heat. The hottest temperature ever recorded on Earth is 57.8 degrees Celsius in northern Africa. But that was just one day. Abnormally high temperatures for days and weeks on end are when heat really kills.
There are many examples of catastrophic heat waves. Chicago in 1995, almost 800 people died. August 2003 in Europe, huge heat wave. Almost 35,000 people lost their lives.
The heat waves on Earth can get pretty nasty, but travel around our own solar system, and things can get downright ugly. Our closest neighbor, Venus, has an endless heat wave that makes our worst temperature spikes look mild.
The surface temperature is hugely hotter than the Earth. It's 900 degrees Fahrenheit, which is enough to melt some metals. So it's just an awful, awful place.
Venus is, on average, around 42 million kilometers closer to the sun than Earth. But that alone isn't the reason it sizzles. Venus has an atmosphere that traps heat and doesn't let it escape. So everything on the surface just cooks. Your oven, at its hottest, probably only gets to 260 degrees Celsius. Now try to imagine a place where the temperatures are almost twice that.
Now, what's 900 degrees like? Well, to find out, I have some items here that you might recognize. Some chickens, a television set, beer, popcorn, some lead bricks, bacon and eggs, a pair of shoes. Let's see what would happen to those items if they were on Venus. Okay, guys, fire that thing up and roll it in here. This is a dust-raw asphalt heater. All it is a big oven that's used to rework the surface of highways. We're going to use it to create the surface of Venus. It's going to put out a lot of heat, so I'm going to get out of here. You guys want to fire this thing up? Well, let's see what we learned on our trip to the surface of Venus. We heated this up to 900 degrees. Obviously, the shoes are ashes. They didn't survive. Neither did the chicken. It's pretty much burnt to an ash. My bacon and eggs, I was looking forward to that, but not now. That's just a smash. Computer monitor, it's all but gone. The lead, though, it's still there. It's in pools, though, instead of bricks. But everything else is pretty much burnt to a crisp. This all shows us that Venus is one mother of a heat wave.
The hottest planet in our solar system is 480 degrees Celsius. But if we journey to other neighborhoods in our galaxy, we go from the frying pan into the blast furnace. And amazingly enough, scientists can tell what the weather is like trillions upon trillions of kilometers away. Scientists use NASA's infrared space telescope, Spitzer, to gauge weather on exosolar or exoplanets, those worlds outside our solar system that orbit their own star. It's a simple technique, like working out the weight of your dog. Weigh yourself holding the dog, then weigh yourself without the dog. Simple subtraction gives you the weight of your pet. Scientists basically do the same thing to detect and study exoplanets. They measure the infrared radiation and visible light emitted from a star. Then, when an exoplanet passes between us and that star, it blocks some of that star's radiation, and they measure it again. The resulting difference is data that helps scientists calculate the size of the exoplanet, its orbit, and its atmospheric conditions.
In some ways, studying these planets is a big exercise in trying to massage a little bit of signal out of this huge glare of star, but it's real.
As technology improves and scientists refine their techniques, we learn more every day about some of the most extreme weather in the cosmos. But as bad as heat can be, there are winds out there that can blow mountains off a map. Sizzling heat can be one of nature's deadliest forces. But at least it's predictable. We can see it coming, and we can usually protect ourselves. But Mother Nature has one nasty bit of business that can come out of nowhere to deliver a catastrophic sucker punch. The wind. This invisible wrecking ball doesn't just kill. Wind can obliterate everything in its path, devastating the landscape and wiping entire towns off the map. But fundamentally, wind is pretty simple.
Wind is caused by the air trying to reach stasis, atmosphere moving from an area of higher pressure to an area of lower pressure.
To better understand wind, just pick up a balloon.
Here's how wind works. It's the atmosphere trying to normalize itself. Inside the balloon, higher pressure. Outside the balloon, lower pressure. When I let the air out, wind.
The larger the pressure differential, the higher the wind speed, and Mother Nature can really step on the gas.
There's a road! Roof! Get on there!
The most violent winds on Earth happen inside tornadoes. Winds here can get as high as 480 kilometers an hour, strong enough to toss around cars and lift buildings off their foundations.
A tornado is the most ferocious and most concentrated area of low pressure on the planet.
Tornadoes form when a huge mass of dry, cold air tries to mix with warm, moist air. This mix creates instability in the atmosphere.
Oh my God! The house is gone! Oh my God!
So how does an instability and temperature difference turn into a raging vortex able to destroy all things in its path, including trees, cars, and even buildings?
If you want to understand how a tornado works, all you need is a little pan of fire. Because you see, tornadoes form when two masses of air come together. A warm, moist layer that's trapped underneath a cooler layer. And as the warm air goes up, as this fire is doing, and the colder layer squeezes in and starts to spin ever so slightly, voila, you get a tornado. And if you look closely at the vortex, you'll notice that it goes faster and faster as it gets smaller. That's called conservation of angular momentum. You can see that throughout the universe, from galaxies down to your toilet bowl.
The deadly power and unpredictability of tornadoes puts them virtually off limits to field study. That's why Dr. Peter Rines creates little ones in his laboratory, inside spinning pools of water.
This is a very simple rendition of a complicated tornado. The goal here is to try to understand how the inflow feeds the tornado.
Water and air are both technically fluids, so they behave in the same way. Dr. Rines starts the experiment by injecting a small amount of fluorescent dye into the bottom, and the tank rotates to match the turbulence of our atmosphere on our spinning Earth. The dye immediately gives us a stunning look at how the water is moving. It heads straight for the mouth of this tornado, revealing the internal structures of nature's most powerful wind event.
The shapes of these dye surfaces encode all of the relative motion of the tornado in a very exact way.
This experiment shows that tornadoes suck up air from the ground and shoot it up the spout. And a tornado's structure isn't only about the vortex. There are also powerful outer layers that spin around this fast-moving core.
The strength of the tornado really is measured by how many of the layers there are. So think of it as like tree rings. How many tree rings do you count? The stronger the tornado, the more layers it's got, because that's a sign of a rapid core rotation.
By understanding a tornado's architecture and how they form, Dr. Rines aims to help predict these deadly events.
I think the major reason for having our severe storms research labs is to be able to predict them and get people warning.
In the United States, there are about 1,000 tornadoes a year, and most form in a region called Tornado Alley. It's a stretch of land running from North Dakota down to Texas, where warm air from the Gulf of Mexico collides with cold air running down from Canada. These colliding air masses can produce enormous twisters and even epidemics of them. That's what happened in April 1974, when a single storm spawned 148 tornadoes. It was called the super outbreak. Twisters were confirmed in 13 different US states, all the way to the Canadian province of Ontario. Never before had so many violent tornadoes been observed in a single weather phenomenon. 30 tornadoes measured F4, or the maximum F5 on the Fujita scale, which rates a twister's intensity. More than 300 people were killed, over 5,000 injured, and almost 28,000 buildings were damaged or destroyed.
It came from just unusually large masses of air that decided to move towards each other. And we had this super collision and lots of smaller collisions within that created this big long band of tornadoes, and they were just popping up into the sky everywhere. It was a pretty dramatic week.
Earth can spawn some savage weather, but it isn't alone. Storms are universal, and the same processes that create windstorms on Earth create massive dust storms on Mars.
The most extreme example of a weather system on Mars are these global dust storms that develop near northern summers and envelop the whole planet with dust.
It's not that the red planet's winds are so much faster than here on Earth. It's that the entire Martian surface is covered in dust. Once that wind starts blowing, particles get kicked up over the entire surface of the planet, and that spells trouble for the Mars rovers.
Dust fills the sky and obscures the sun from the solar panels, making it difficult for the batteries of the rovers to charge up.
Without the energy provided by the solar panels, the rovers would have died on Mars a long time ago. But there's another amazing wind event that comes along to revive the rovers.
There are dust devils on Mars. The rovers have actually taken snapshots all in a row, and you can actually see the dust devil moving across, which is pretty cool.
These fast-moving dust devils, similar to tornadoes on Earth, come along to blow the dust off the solar panels.
Thank God for a windy day.
But the violent 480 km/h bursts of a tornado aren't actually Earth's most powerful weather. The greatest damage occurs when you change the recipe for weather disaster by just adding water. Hurricanes. One of these storms can generate more energy than every power plant on Earth combined.
A few things need to occur for a hurricane. Tranquil, warm ocean water. Gentle but consistent winds.
Warm air rising from the ocean's surface draws water vapor with it and forms thunderstorms. As winds drive the storm across the ocean, Earth's rotation helps the storm turn into a spinning mass. Spiraling bands of rain develop, and when the wind speeds hit 120 kilometers an hour, it's a hurricane. These intense winds push the surface of the ocean far above normal levels. This is called the storm surge, and it's often the most destructive element of a hurricane. During the tragic devastation of Hurricane Katrina, the storm surge was 8.5 meters above sea level.
You have the force of the hurricane, which is pushing a wave of water ahead of it. It's a 15 to 20-foot storm surge. You have the very delicate coastal circumstances along the Gulf Coast, including New Orleans, which is below sea level, and it was a recipe for disaster.
Scientists have calculated that the average hurricane dumps 21.3 billion cubic meters of rain a day. Enough water to fill 22 million Olympic swimming pools. And the process of condensation that turns water vapor into rain generates heat energy, a lot of energy. Try 600 trillion watts a day. That's equivalent to detonating a 10 megaton nuclear bomb every 20 minutes. But relatively speaking, there are hurricanes out there in the solar system that make our worst storms on Earth look like a blip on the Doppler radar.
If your weekend plans include Neptune, well, it's cold, minus 330 degrees. Plus, you have 1,100 mile-an-hour winds. So, lip balm, keep your children and your pets on leashes.
About 4.5 billion kilometers from the sun, Neptune gets very little heat from our star. So it's frigid on the outside, but it's still a furnace on the inside. And just like on Earth, that temperature disparity creates weather. Very unpleasant weather.
There's actually a giant storm on Neptune called the Great Dark Spot. It's a big storm about the size of the Earth, and it's persisted for many years. The winds amazingly get up to 1,100 miles an hour. The temperature of its cloud tops is about minus 260 degrees Fahrenheit. That low temperature means there's very little friction and very little turbulence. All the winds can just keep going and going faster and faster.
So it's really an incredibly violent place, not really where you want to spend your summer vacation.
The largest hurricanes in our cosmic neighborhood can be found on the solar system's largest planet.
The storms on the planet Jupiter just boggle the mind.
Like weather here on Earth, weather on Jupiter is caused by temperature differentials.
It does get heat from the sun, but in fact, most of the heat from Jupiter is coming from the inside. The center of Jupiter is very hot, and even after all this time, even after 4.5 billion years, that heat is radiating away.
The temperature differential between Jupiter's hot core and frigid atmospheric temperature, averaging minus 110 degrees Celsius, creates epic storms.
The storms on Jupiter are just a completely different order than the storms on Earth. First is how long they last. Galileo saw the Great Red Spot on Jupiter 400 years ago, and it's still there today.
It's about 3 times the size of the Earth. Now, amazingly, this storm never stops. A hurricane on Earth eventually moves over some land where it loses energy. On Jupiter, there is no land. There's nothing really to stop the storm.
This massive storm, big enough to swallow 3 Earths, spins in Jupiter's atmosphere. But because the planet is a gas giant, it doesn't have a solid surface, and no one knows quite how deep down it reaches.
The maximum speed in these storms on Jupiter is about 500 miles an hour. and the most savage hurricanes we have don't reach 200 miles an hour.
Could humans even survive a storm like that? Not if we make the mistake of venturing outside.
Jupiter. It's big, and boy, is it windy. The winds there blow 400 to 500 miles per hour, and that's enough to really blow your hair back. Now, what's 500 miles per hour like? Well, here's my friend Dan, and he brought his sandblasting rig, and we're going to show you. Have at it, buddy. A 500 mile per hour wind is just shredding the wood. I've never seen anything quite like this. Wow! See, it cut right through there, didn't it? Now, can we try something else? Okay. Like a chicken? Can we cut a chicken with that thing? Why not? I'm going to go get a chicken. Hang on just a second. I'll be right back. I've never done anything like this. A chicken for you, Dan, on Jupiter. Go for it. That's good. That's good. Oh, my gosh. Dan, did you see what you did to this thing? Well, that's nasty. But it does go to show that the winds on Jupiter could tear flesh from bones. And we have nothing like this on Earth. It's gross. Yeah.
But how could a storm with winds that strong last for hundreds, possibly thousands of years? To find out, Dr. Peter Rines is using another water tank to recreate this epic storm.
We were really surprised in this very simple thing we can do in the laboratory with our spinning platforms, that we can actually reproduce the interactions that give you very long-lived structures like the Great Red Spot.
In his experiment, the bowl of water represents Jupiter's atmosphere, and the spin mimics the planet's massive rotation. The colored dye represents the formation of a storm.
By simply swooshing a paddle through the water, we create a great chaotic thing. But it doesn't stay chaotic for very long because the rotation of the planet sorts out structures and creates a nice big round storm.
Rines found out that rotation not only organized the storm, but nurtured it, capturing the energy emanating from Jupiter's interior to feed the storm indefinitely.
What the planet's rotation does is it preserves the energy and sends it out to these large storms where it's preserved for very long times. So you've got a 400-year-old red spot.
From our vantage point, Jupiter is one of the most beautiful sights in the sky, but that beauty hides a frightening beast. Imagine a storm with the ferocity of the Great Red Spot forming on Earth. A large city like Paris would not do so well in an 800-kilometer-an-hour hurricane. We're talking complete and utter devastation. The taller structures would be the first to go. Eventually, every building would be leveled. And Paris would be scrubbed off the map. Perhaps we should consider ourselves lucky. As bad as weather gets here on Earth, occasionally we need to remind ourselves that we've got it good. And what's really amazing is that those intense storms out in our solar system are actually quite familiar. The weather might be exponentially larger, more extreme, but we can comprehend it because we've got similar weather events here on Earth. But there's some bizarre weather out there that's almost incomprehensible, because the universe's weirdest weather is truly mind-boggling. Here on Earth, we've got weather extremes, and some of it seems pretty weird. But the fact is, there's nothing we haven't seen before. Unpredictable, sure, but no huge mysteries. We've pretty much figured out all the weather we've got. But when you leave Earth, the picture gets a little cloudy, because there's some seriously bizarre weather out there. Take, for example, Saturn's largest moon, Titan.
It's a crazy place. It's an almost Earth-like feel to it with this atmosphere and the clouds and the rain, but every time you look at it more closely, you realize this is a very strange place. It's not like the Earth that I'm used to.
There were theories about Titan, but no one knew what it was really like because it's surrounded by a thick, hazy atmosphere, and we couldn't get a good look at it. But in 2005, we landed a probe on Titan, the farthest world from Earth we've ever touched, and from an amazing 1,200 million kilometers away, the probe sent back pictures.
It was one of the most fun days I can remember in my scientific life, was this day that this was happening. We had a pool in the Planetary Sciences Department here at Caltech where everybody got to predict what was going to happen when the Huygens probe landed. And the predictions ranged from it's going to land in a liquid and float, it's going to be destroyed. Somebody suggested it was going to get eaten. That one didn't happen. Nobody expected what we saw.
What they saw was a world sculpted by weather. Photographs of mountain ranges and shorelines, dunes and riverbeds, all created by wind and rain.
We sat there in the room watching these come down, and the entire floor that is the Caltech Planetary Science Department was just silent and in awe.
But Titan's landscape wasn't carved by water. It's methane, the main component of Earth's natural gas. On Titan, at minus 180 degrees Celsius, it's a liquid. And Titan's methane goes through a cycle, just like our water here on Earth. Evaporation leads to clouds, which leads to precipitation. And that methane rain creates rivers, streams, and massive lakes, even bigger than the Great Lakes.
The liquid methane comes from rain up in the sky. If the clouds are up in the sky, the clouds are frozen droplets of methane instead of water. And those frozen droplets of methane then rain down onto the surface.
Maybe you're planning a trip to one of Saturn's moons. One I would avoid would be Titan. Partly cloudy, 80% chance of liquid methane showers that will freeze you in place. Goosebumps will be the least of your problems. And highs will be in the mid to upper minus 300s.
The weather on Titan is a bit chilly. Now, this really isn't liquid methane, it's liquid nitrogen, but it's about the same temperature, 300 degrees below zero. Let's see what would happen to, say, a flower if it was rained on Titan. I'll put it in the liquid nitrogen. It's almost like crushing glass. That's cold. Let's try a banana. Wow. The rain on Titan is so cold it would freeze anything on Earth solid. So you probably wouldn't want to get caught in one of those rainstorms.
A deluge of freezing liquid methane. This is not the kind of rain that an umbrella could protect you from. But Titan is just one place with weird weather. The planet it circles, Saturn, has some even more extreme atmospheric conditions.
Saturn also has these giant hurricane-like storms, including one around the South Pole. And around the North Pole, there's a very strange formation. Nobody really understands what's going on.
Here on Earth, our biggest storms form circles and spirals. The North Pole of Saturn features a gigantic storm with an amazing geometric design. It's a perfect hexagon with 6 very distinct sides and angles. But Saturn has one feature that takes one of Earth's weirdest and most dangerous weather events and multiplies it by 10,000. Lightning. Scientists aren't exactly sure how lightning forms, but the most common theory is that positive and negative electrical charges build up in the clouds. And like the pressure differentials that cause wind, when the difference between the positive and negative charges gets too large, Mother Nature steps in to balance the books. A surge of electricity flows between the charges to even things out. This is lightning. Our lightning bolts generally contain about 100 million volts of electricity, flowing at 320 million kilometers an hour. But this is nothing compared to Saturn's biggest bolts.
There are also enormous thunderstorms that occur in Saturn, where the lightning bolts are about 10,000 times the strength of the strongest lightning bolts on Earth.
And yet, as intensely bizarre as weather can be in our solar system, scientists have found another exoplanet that makes our neighborhood's wildest and weirdest seem pretty tame.
The planet Corot B is unimaginably hotter than the Earth.
Exoplanet Corot 7b, 400 light-years away, is a rocky planet about twice the size of Earth. But we're over 149 million kilometers from our sun. Corot 7b is only 2.4 million kilometers from its sun, and zipping through space at 200 kilometers a second, its year lasts only 20 hours.
If you were on the surface of a planet like Corot 7b, it's hard to imagine what it would be like. At such high temperatures, things that we think of as solids, metals, would be liquid.
With surface temperatures on this rocky planet reaching 1,650 degrees Celsius, this exoplanet has weather right out of a science fiction movie. Scientists suspect its surface is covered with rivers and lakes of molten minerals, like lava or lead, with a chance of showers of liquefied zinc. Methane rain will freeze you solid. Boiling molten rain will melt you. Either way, it's still rain, and we know how it's going to behave, because weather is fundamentally the same everywhere in the universe. The conditions and elements might be exotic, but it's just weather. The good news is that chances are very slim that we'll ever set foot on any of these remote planets soon. But the bad news is that truly cataclysmic storms could come to us right here on Earth.
If one of these were to happen today, people are really worried, actually. It would shut the world down.
We've seen stunning storms here on Earth and billions of kilometers away. But some of the most powerful and violent storms ever detected are right in the middle of our solar system, on the sun.
We can talk about weather on the surface of the sun because the sun has an atmosphere, if you will. There are huge eruptions of magnetic fields which lend lots of drama to the surface of the sun and can expel huge numbers of particles towards the Earth. We call these solar storms.
And these storms affect Earth and the other planets in our solar system because we're actually in the sun's atmosphere. And solar weather can have a dramatic impact on Earth. Take, for example, solar flares.
The amount of energy that's released in a solar flare is beyond human comprehension. These are mind-numbing energies. You could take all of the combined nuclear weapons on the entire planet, and a single solar flare would blow those out of the water.
Just beneath the surface of the sun, massive currents of hot plasma create electrically charged ions and electrons. The motions of these electrical currents generates magnetism, and the sun is covered with a web of magnetic fields. If a couple of these field lines get tangled up, they twist and stretch until they finally snap and explode. As these colossal flares rocket upwards, they can reach the unimaginable temperature of 44 million degrees Celsius. But solar flares aren't the worst of the sun's stormy weather.
If solar flares are the tornadoes of solar storms, a coronal mass ejection is a hurricane. This is not something that is focused in a small spot. This is a gigantic explosion. And this blasts out billions of tons of subatomic particles in a huge puffball that goes out into the solar system.
Sometimes, one of the snapping field lines of a solar flare triggers a titanic chain reaction. It's called a coronal mass ejection, or CME. And believe it or not, it has something in common with mousetraps and ping pong balls.
300 mousetraps, all set with ping pong balls ready to go. The spring in each one of these mousetraps is storing a lot of potential energy, just like a magnetic field line right about to break. And when it does, watch out. That's the same thing that happens during a coronal mass ejection. But instead of shooting out ping pong balls, the sun shoots out billions of tons of gas and charged particles. Amazing.
During that chain reaction, the sun unleashes billions of tons of superheated plasma, an electrified cloud of gas, up to 8 million kilometers an hour. When it hits the Earth, it packs such a wallop that it compresses the Earth's magnetosphere, the magnetic field that circles Earth and protects us from most space weather. And when the magnetosphere snaps back into shape, it releases trillions of watts of electricity. This current floods the Earth, wreaking havoc with technology everywhere.
The most serious example in modern times was in 1859, when a huge solar flare swept over the Earth and induced such huge currents in the Earth's magnetic field that it set telegraph offices on fire. Guys sitting in their telegraph offices just boom, spun up in smoke. If one of these were to happen today, it would shut the world down.
Scientists at the National Solar Observatory spend all their time staring at the sun. More specifically, the sun's atmosphere, also called the corona.
And the corona is really a vast atmosphere that starts just above the surface.
It's a cloud of plasma, superheated gas that envelops the sun. Temperatures here are a searing 1.1 million degrees Celsius. That's 200 times hotter than the surface of the sun. So how does this superheated cloud affect us here on Earth? That's one of the questions these scientists are trying to answer. They're using a special telescope that creates an artificial eclipse to block out the entire body of the sun, leaving only the corona visible. By doing this, these researchers can monitor changes in the corona and gauge the threat any fluctuations pose to Earth. Because we're so close to the sun, any changes can be dangerous.
We're within the corona of the sun, right here on Earth, actually. We're within this area, and it's called the heliosphere. That's the domain of the sun.
Even though Earth exists in this solar atmosphere, we've got a protective shield.
Of course, our magnetosphere protects us from the solar wind. The heliosphere, in turn, protects us from the cosmic rays that are coming from the center of the galaxy. We have our magnetosphere, which is our shield, and then the solar system has the heliosphere, which is the shield for all of the solar system. The sun is extremely important to us. It's extremely important.
But just as our own atmosphere can turn violent, so can the sun's. Alexei Petsov studies sunspots. They're magnetic storms that produce some of the sun's most terrible weather, like solar flares and coronal mass ejections. He's using a specialized telescope that will allow him to see not just the sunspot, but what's going on inside it.
It allows us to look through the atmosphere of, say, sunspot and see what is the three-dimensional structure, see where certain processes take place.
Looking into a sunspot, Petsov can see details that might one day allow scientists to better predict an onslaught of solar weather.
Eventually, we'll be able to understand how some of these processes occur and what triggers them.
If a solar storm like that 1859 event occurred today, scientists calculate that it could cause over $1 trillion in damages, 10 times worse than the aftermath of Hurricane Katrina.
If the sun were to have a really bad flare, it just decided to really belch out something nasty, and that came down and hit the Earth, that could fry a lot of our satellites. And that means no GPS. That means no communications.
It would short-circuit power grids all over the Earth. Probably most of the Earth would be plunged into darkness.
However, this group of scientists is trying to keep our lights on in such an event.
Looking at the most current EIT indicates kind of a weak coronal hole up here that we're looking at, possibly affecting the Earth's geomagnetic field in about a week or so. Keep an eye on it.
Very basically, we're forecasting space weather. We're looking at the dynamics on the sun, things constantly changing, coronal mass ejections, big flares.
The Space Weather Prediction Center is staring at the sun 24/7, looking for any signs of cataclysmic solar activity that could devastate Earth.
The ultimate goal is to put a forecast out for our users that can be affected by the sun, to give them an idea for the next 10 minutes, 3 days, 10 years of what we think the sun's going to be doing to their system.
Some solar storms travel at almost the speed of light, reaching Earth in minutes. But even a few minutes of advanced warning might help avert a disaster.
So we'll put out a forecast that we believe the geomagnetic field is going to be a certain way. And if your system is sensitive to geomagnetic fluctuations, then, take caution or do whatever you have to do.
Ultimately, forecasting space weather is just as much of a guessing game as forecasting weather back home.
I love using satellites. I love using all the data that comes off the satellites. But the actual instrument that I use that is my fail-safe instrument is this little crystal ball right here.
Forecasting any kind of weather is as much art as it is science. There are too many variables in the equation. The elements might be wildly different, but the storms that Mother Nature cooks up here on Earth and in the farthest corners of the universe are fundamentally the same. In fact, if we ever do get a chance to meet some aliens from another part of the galaxy, at least we'll have one thing in common to talk about. A good icebreaker might be, how's the weather?